Hi, I'm Mrs. Bricky, and this video is for uh, Unit 7, Lesson 1. We're going to be graphing absolute value functions. You have probably dealt with absolute value before as an operator, so now we're going to be graphing functions where the function itself includes the absolute value operator, sort of like f of x is equal to the absolute value of x. We are going to start with these two functions. G of x is equal to the absolute value of x minus 5, and f of x is equal to negative 2 multiplied by the absolute value of x minus 1 plus 4. We're just going to be evaluating these functions to start with, and then we'll get to graphing in a minute. So if we want to know what g of 2 is, that means that we need to substitute 2 into the function in place of x. So g of 2 would be the absolute value of 2 minus 5. Well, 2 minus 5 is equal to negative 3. So this is the absolute value of negative 3, which gives me 3. So when you're evaluating an absolute value function like this, you do want to pay attention to the order of operations. So we did need to do the subtraction first and then take the absolute value of the result. So g of 9, we would be taking the absolute value of 9 minus 5, and this would be the absolute value of 4, which is 4. For g of negative 2, we are taking the absolute value of negative 2 minus 5. Well, that's the same as the absolute value of negative 7, which is 7. Let's move to function f here. F of 3 is negative 2 multiplied by the absolute value of 3 minus 1 plus 4. So this is negative 2 multiplied by the absolute value of 2 plus 4. Well, that's a negative 4 plus 4, so this result is 0. Now let's sub in 0 in place of x. F of 0 is equal to negative 2 multiplied by 0 minus 1 plus 4. Well, this is the absolute value of negative 1 right here inside. We have a negative 1, so absolute value of negative 1 is positive 1. So this is negative 2 plus 4. So we're taking a positive 1. Right here, we've got a positive 1. We're multiplying that by a negative 2, so we get negative 2 as our result. Negative 2 plus 4 gives me a result of positive 2. Let's do one more, f of negative 3. That would be negative 2 multiplied by the absolute value of negative 3 minus 1, and then we need to add 4. So this is a negative 2, and inside my absolute value, I have a negative 4, but that just means that it's a positive 4. So this is a negative 8 plus 4. Our result here is negative 4. Now, sometimes people worry, like, if I have a function that has absolute value, how can I get a negative result? Well, we definitely can get a negative result in this function because we're multiplying by a negative 2. So nothing to worry about there. Just because a function includes an absolute value operator does not mean that you're guaranteed to get positive results. It just means that you're going to take an absolute value at some point when you're evaluating. Now, I wrote out a lot of steps on these last couple. You may be doing some of those steps in your head as you're working out. You don't necessarily need to show all of these steps. Some of them you might do mentally, and that's fine. Okay, so we're going to do some graphs. Now, these first couple of graphs we're going to do just using a table of values and plotting points. So our very most basic absolute value function is the function y is equal to the absolute value of x. And so we just want to evaluate each of these. So for each entry in this column here, we're just going to take the absolute value of the x value. So this would be 2. The absolute value of negative 1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1, and the absolute value of 2 is 2. So this gives me a collection of points that I can plot. Negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. And just from those points, you can see that we kind of have a shape forming. And if you think about the absolute value of -3, it's 3, and the absolute value of 3 is 3. So we have some symmetry happening here. And you can see that we sort of get this V shape for our graph. This point right here, that sharp turn right there, is called the vertex of the graph. So for this particular function, the vertex is at the point 0, 0, which is the origin. And that vertex is always going to represent the highest or the lowest point on the graph. So for this graph, that's the lowest point. Let's try another function. So this is our function f from before. So we actually already evaluated f of 0 and got 2, and we evaluated f of 3 and got 0. So let's evaluate a couple more x values to see what this shape might be, to see if we can see some connections. So if we substitute -2 in to the function, we have -2 multiplied by 3. This is an absolute value of -3, so that's a 3. So that's a -6 plus 4. That's -2. And go ahead and plot that. See, we also have this point and this point. So it's not super clear yet what shape we have, but we'll add a couple more points to help us see it. So let's sub in -1. Well, in that absolute value, we have a -2. So this is a +2 multiplied by -2 plus 4. That is 0. Let's sub in 1. -2 multiplied by the absolute value of 1 minus 1 plus 4. Well, this is 0, so our result is 4. 1, 4. And finally, we're going to substitute the value 2 in. -2 times 2 minus 1 absolute value plus 4. Well, this is a 1, so this is a -2 times 1 plus 4. That gives me an output of 2. So I go through the point 2, 2 as well. Now, if you weren't sure what shape the graph was going to make, you could plug in some more x values, but it looks like we have sort of a V shape here as well, but this time our V is upside down. There's our shape of our function f. And again, it has a vertex. This point right here is called the vertex. For this function, that represents the highest point of the graph. Okay, so how is this graph of f of x related to the graph of the parent function? Well, our graph that we did first had a vertex at the origin, and the slope, which we're going to count on the right side of the v, the slope is just up 1 over 1, so that's a slope of 1. Our function f that we just graphed has the vertex of 1, 4. And its slope, if we look at the slope of the right side of the graph, it looks like it's going down 2 over 1, down 2 over 1. So that's a slope of -2. So looking at these equations, can you see evidence of the vertex and the slope in the equation, especially if you compare it to the basic parent function? Well, hopefully you're noticing that we can see the vertex's coordinates right there in the function. There's the 1 and the 4. And then we also can see evidence of the slope. And that matches the original parent function. It's just that we don't see the 1s and the 0s written. Another way of writing this, though, would be 1 times the absolute value of, x minus 0 plus 0. So you can see that if I fill in some zeros here, there's the vertex, and then here's the slope. And, this is just another way of, an unsimplified way of writing the absolute value of x. So instead of, doing this process of filling in a table of values and evaluating each time, we can use this idea of looking for evidence in the equation to decide how to graph the function. And this is just a little bit faster way than filling in a table of values. But of course, you could always use a table of values if you were stuck. So when we look at the absolute value function, we're going to see the vertical stretch right here as a coefficient of the absolute value. That stretch can be positive or negative, and it's going to give you the slope of the right side of the line. Now, the two sides of the absolute value are symmetric, and we'll practice graphing that in a second. And then you'll see a number subtracted from x. That's going to give you the x coordinate of the vertex. And then you'll see a constant that can be added or subtracted. So this k can be positive or negative, and that gives you the y coordinate of the vertex. So probably the trickiest part about this for people is that, this equation or this base form of the equation includes the minus here. So if it says, x minus 5, the h is the 5, not negative 5. It is positive 5. But if it said x plus 5, then we would consider that to be a negative h value. Anyway, you'll get much better at this with practice. So that's just the one thing to be careful of is if we see it's an x minus a number, so we have to be careful about the sign of the h. So for these first three functions right here, we're just going to identify the location of the vertex. So for this function, it's going to be at -7, -12. And again, the reason it's -7 is that this x plus 7 is the same as x minus a -7. The x minus is part of the function's form, and so this is a -7 here. That's our h value. For our next function g, the vertex is at +5, 0. Now we don't see that +0 written at the end, so we just have to recognize that if there's not a constant there, then that k value that's being added is a 0. And then finally, this is just a regular absolute value of x. It doesn't have minus a number with it, so the vertex has an x coordinate of 0, and then the k value, the y coordinate of the vertex, is 8. So that one has a vertex at 0, 8. You will get very, very good at this by the end of the unit. Okay, if you have a paper assignment, you can do those first few problems for practice. When a is a negative number, when that vertical stretch is negative, we say that the function is vertically reflected. So if that V shape is opening downward, like this blue example on the screen, we say that function was reflected. The vertex of the absolute value is the location of the highest or lowest value. In math, we call those minimum and maximum values. So if you have a function like my function f here that is not reflected, it's just that regular V shape, then the function has a minimum value. And you can see that the minimum value of this one is 4. That's the lowest y value that function takes on. And if we have a reflected function like function g, that function has a maximum or highest value, and you can see that this function has a maximum value of 3. So we will, and when you're asked for a maximum or minimum value, you are being asked for a y value. So we're going to practice graphing a couple of functions by using the vertex and the stretch. So for our first function here, function f of x is equal to -1/2 times the absolute value of x minus 2 plus 3. So the vertex here you can see is at 2, 3. The 2 comes from this number 2 that's being subtracted from x, and the 3 is that constant at the end. So here's our vertex. The slope, or the vertical stretch, is that coefficient, -1/2. So going to the right, I'm going to count down 1 over 2, down 1 over 2, down 1 over 2. Now that gives me the right side of the absolute value function. we have to go backwards to get the other side. When you're graphing these, make sure that you do get a V shape. Every once in a while, somebody will just not count it the backwards way correctly, and they'll end up with a line. So just make sure that when you finish that you have that V shape. You can see that this is a reflected V shape, so our function is reflected, and our maximum value is 3. You can see that 3 is the highest value of the graph. Okay, our next function is the absolute value of x plus 4 minus 2. So the vertex of this function is at -4, -2. Remember that it's x minus h, so since we have an x plus 4 here, that's the same as x minus -4. So that's why we have a -4 as our x coordinate of our vertex. So -4, -2 is right here. The stretch or the slope we see as a coefficient. And so for my function that I'm graphing right now, that's just a coefficient of 1, which is unwritten. So our slope is up 1 over 1. So we're going to count that out to the right side. That's one side of our V shape. And then we'll just go backwards to get the other side. Back 1, up 1. And you should see symmetry here. You know, that vertex is sort of, if you reflect the function across the vertex, you should see that the two sides are the same. Okay, is this graph reflected vertically? It is not. It's an upward V shape. Now, this one, I guess you could say, kind of looks like maybe a check mark. Just depending on where the vertex is, the two sides, you know, they might not extend the same amount, but if we shifted our coordinate system or if we had more space, then you would definitely see that V shape. So don't worry about if, you know, if it looks like a check mark or something, that's still a V-shaped graph. This one has a lowest or minimum value, and our lowest minimum value here is -2. Okay, our next function is 3/2, absolute x minus 1, subtract 5. So our vertex for this function is at 1, -5. So here's our vertex. And the stretch of this is 3/2. So we're going to count the slope up 3 over 2. Up 3 over 2. So here's one side of our absolute value. And then we'll go backwards, up 3 backwards 2 to get the other side of that V shape. This one's kind of nice and symmetric. This graph is not reflected vertically. It is an upward V, and it has a minimum value of -5. That's the lowest value on the graph. So the domain of this function, now we practiced domain and range before Christmas break. If you remember, for domain, it's the x values that graph includes, and it is written from left to right. Well, this one is going off to the left and off to the right, so our domain is -infinity to +infinity. If you like, there is a symbol that we can use. It's an R that has 2 bars like this. That symbol means all real numbers. So it basically just means all of the numbers from -infinity to +infinity. So you kind of can write the domain either of those ways. You can write it in interval notation with that parenthesis -infinity, +infinity, or you can write it with this all real numbers symbol. Now, the range of this function is not the same. It's not -infinity to +infinity. Remember, we have a minimum value here. We have a lowest point. The range is the y values of the graph, and we read this from the bottom to the top. So our lowest value is -5. and then it goes up to infinity. We do want to use a bracket on the -5 because we are including that number as part of our range. It is part of the graph. It's in fact the vertex of the graph. Okay, this graph is f of x is equal to negative absolute x plus 4. So our vertex is at 0, 4. And the slope here, which is the coefficient, is a -1. We don't see the 1 written because math people decided they didn't need to write it, but it is -1. So we're going down 1 over 1, down 1 over 1 to get the right side of the graph, and then we'll just do that backwards to get the left side of the V. And that stretch, that vertical stretch, was a negative number, so you can see that we do have a, sorry, I don't know why, but when I do this on a tablet, sometimes it's wavy. We do have a reflected graph. So this one has a maximum value, and the maximum value is 4. That's the highest y value. Just like our other graph, the domain is from -infinity to +infinity, or you can use the all real number symbol. And the range, we write ranges from the bottom to the top, from the lowest to the highest. We don't have a lowest value here. These two sides are continuing down if we extended our graph. So our range is from -infinity up to a highest value of 4. Okay, if you have a paper assignment, you can practice some graphs by yourself. So now we're just going to reverse that process. We're going to use a picture of the function to write its equation. So our vertex of our first graph is at 5, -1. And if we count off that slope, it looks like the right side of the graph is just going up 1 over 1. So in our equation, we'll have y equals, our slope for this graph is a 1, so we don't need to write the 1. If you want to write it, you can, but it's not necessary. So absolute x minus 5, we'll end our absolute value there. And then our k value is -1, so we can do a -1. You could, if you want to do right, plus -1, but that would just simplify to -1. Okay, so our function is y equals absolute value x minus 5 plus, -1. Okay, here's our next one. You can see that the vertex of this function is at -1, -3. And if we count the slope of the right side of the graph, let's see, it looks like it's going down 3 over 2. So that's a slope of -3/2. So our equation is y equals -3/2 absolute x plus 1 minus 3. Now that plus 1 came from x minus -1, and if we simplify that, it becomes an x plus 1. Okay, so our last graph to write the equation of has a vertex at -2, 0. And the slope here is, it looks like up 1 over 4, so slope of 1/4. So writing our equation, we get y is equal to, we put our stretch first, 1/4. This is going to be an x plus 2, and then we don't really need to write that plus 0 because plus 0 just doesn't change it. So simplified, we don't need that plus 0 there. Okay, we can think of absolute value graphs as being translated compared to the parent function, which is having the vertex at the origin. So what we want to do here, this is our last problem, we want to write the equation for an absolute value function which has been translated 4 units to the right, 1, 2, 3, 4, and up 2 units, 1, 2, from the origin. So on your paper, you didn't have a fancy V that you could move around, but you can imagine just, starting at that origin and then counting we're going to go 4 to the right and 2 up to find the new location of your vertex. Okay, so the equation of this function would be y is equal to, and our absolute value function is just a stretch of 1, so we don't need to write any kind of stretch there. And this would be an x minus 4 plus 2. So we would say in this case that the horizontal translation, so horizontal is left and right, so this is right 4, and the vertical translation, so vertical would be how much it shifted up or down. This would be a vertical translation of up 2. Okay,